Let's begin. No quiz today. Not because I'm like so nice, it's because I totally forgot. It's Thursday. And again, I was, designing the slides while driving. Don't, we need a word for like don't, drink and drive. Don't like drive and derive or something like that. So something funny like that. So yeah, I totally forgot. And my apologies about that. I know how much you love quizzes. So please don't complain about that and the feedback saying that Dr. Saad didn't consistently give us quizzes every Thursday and he missed that one Thursday, so I appreciate that. The exam one is now behind us, and I am working on grading that. As you know, essay questions, I always shoot myself in the foot by asking essay questions because I have to grade each and every one separately, one by one. So that's a lot. We got 6 essay questions, about 50 students, so 300 questions that I have to grade. So be patient with me, please, and I will release the grades as once I'm done grading those. I'm planning on getting you a small homework assignment by today or tomorrow. I'll give you exactly 1 week for it. It will be a lightweight assignment, maybe a derivation, because with the central limit theorem, which we're just finishing up, it's mostly about theory, right? So there will be a theoretical derivation that I will ask you to do. We are done with I need like 10 more minutes to seal off the central limit theorem, and then we will embark on Unit 3, on Part 3 of the course, which is Inferential Statistics, exactly that's what we've been waiting for, and it's exciting stuff. To wrap up the central limit theorem, if you remember what we did before the exam and what we did together in class, when we were talking about drawing samples from a population, and why do we focus on samples from a population to study samples? Because in reality, we want to infer something about the population without studying the entire population. We just want to study samples from the population and make a decision about the population, a property about the population, the average height, the average age for heart disease, etc., rate of growth of cancer cells and whatnot, and so on. A lot of stuff can be done just from samples. So the central limit theorem and what we studied there focuses on how do samples behave, what is the distribution of samples, we call that the sampling distribution. We focused on the mean, sampling distribution of sample means, because means are going to be important about a population, the average height, the average rate of cancer growth, etc., the average error in your design for some component in a car, and so on. And together we did this beautiful statistical simulation where we drew, where we rolled a die 1,000 times or 300 times, and then we drew samples of 5 and 10 and 30 and took their mean and plotted the means. And in all cases, we started approaching a normal distribution for the sampling distribution of sample means. So if you were to plot the histogram of the sample means of all the samples drawn, so the x-axis is the mean value of each the samples, and you do a histogram, and you're going to get a normal distribution. And that occurred regardless of the population distribution of the original population. So whether the die is fair, where you have a uniform distribution for that population of the 300 rolls, or like we also did in class, it's biased on one end or another, or if it's normal, any distribution of the population, the sampling distribution of sample means is always normal. This is one of the most beautiful and amazing results in statistics. It is universal. Okay. Now, the sampling distribution of sample means has its own variance because it is a distribution. The means are going to be distributed according to a normal distribution, and we saw that, plotted that. Now, one other question one might ask, which is what is another statistic one might be interested in about a population, and that's the standard deviation or the variance of the population. So we could also ask the question, what is the sampling distribution of sample variances? So I'm going to take these samples again, and instead of computing the mean, I'm going to compute their variance. Okay? I'm going to compute their variance and then do a histogram of the variances. Okay? So this is different than the variance of the sampling distribution of sample means. The sampling distribution of sample means it's its own thing. It has its own variance. Okay? And that's it. The sampling distribution of sample variances, on the x-axis, you're plotting the value of the variance. You're binning it in a histogram, and it's going to have its own variance. So it's the variance of variances. Okay? Now the question, what do you think we will get? Are we going to get a normal distribution for sample variances? Do you think we will get a normal distribution for sample variances? I don't know. I hope so, because it simplifies things. I don't know. How about we run a simulation and see what we get? This is less intuitive than what we did with the sample means, where together we were thinking about rolling a die and we started binning them intuitively, if you remember. This is going to be different. It's actually harder to conceptualize intuitively. Okay? So we're going to run a simulation. Grab your Jupyter notebooks. There will be a few things that I'll need to introduce to you, because we're not going to do it with a die anymore. We're actually going to do it with a full population. And I'll explain that once you get your Jupyter notebooks up and running. Okay? So again, our objective in this simulation is to draw samples from a population, calculate the variance of each sample, and then do a histogram of those sample variances and see if a pattern emerges. Or is it going to be normal, or is it going to be something else? Okay? So let's do that. Grab your Jupyter notebooks. And along the way, I will introduce some NumPy and SciPy utilities. All right. So create a new Jupyter notebook. Let me see. Okay, I'm going to do a new Jupyter notebook, and I'm going to drag it over here. Right? Let me see. Okay, so let's call this in class statistical simulation of sample means. Sample variances. Sample variances. Okay. And as you probably noticed, and you will notice, things are going to pick up faster. We're dealing with continuous math. There's a lot of symbols and formulas we're using. So make sure you're on top of those things. What do we mean by expectation, variance, and so on? Make sure you know at least where to find those formulas if you're confused. But yeah, we're gonna start going faster. Okay, so first I need to grab my boilerplate. So I'm gonna grab this from the simulation we did last time. Just copy paste. I'm importing NumPy, matplotlib, scipy.stats, giving them nicknames, and this cute little thing here to give us beautiful plots. All right. Now, before we begin, I'm going to start by declaring some parameters for the statistical simulation. I want to draw a number of samples. As defined the number of samples, I'm going to do 100,000 because I now want to look in the limit of all samples. You know what's happening when we draw a large number of samples. I don't want to. We can already prove that we need a large number of samples to demonstrate a theorem or a theory. So I'm looking for what happens in the limit. What is asymptotically going to happen when we have a large number of samples, all samples essentially. But the sample size, I'm going to vary that. Sample size, we're going to start with 10, go to 20, 100 maybe, and see what happens, okay? We can start with 5, actually. And now, what are we experimenting with? It is not going to be it's not going to be a die, okay? I just need something, I just need a probability distribution for the population. Now, because unfortunately, the sampling distribution of sample variances has some issues, I need to start the simulation by drawing from a population that is normally distributed. So that is going to be the first condition we're going to work with. I'm going to assume that the population is normally distributed. I can make a die that's normally distributed, but I have 6 probabilities. It looks weird. So how about we just create a population with a normal distribution, a normal distribution, and just sample from that normal distribution. This will introduce a couple of features for you in how to do sampling, more advanced sampling in Python, okay? So we're going to draw random samples from a normal distribution, and I'm going to store those. In samples, and in a variable called samples. The way I get this, I can get it from scipy.stats, but it's ugly and annoying. And a faster and cleaner way is doing it from NumPy. So NumPy and scipy, they work really well together. Some things I use NumPy because it's more convenient, cleaner, the interface is better programmatically. Some other things we do with scipy. So plotting the distribution and doing like PDF, CDF stuff we're doing with scipy.stats, but all the random sampling is going to be done with NumPy. They work very well together. All right, so if I go to the random module in NumPy, if you click NumPy np.random and press Shift Tab, and then if you type normal over here, what this routine does, it draws random samples from a normal distribution. Okay? So what that does for me is it assumes I have a population that is normally distributed, and I'm going to randomly pick values from that distribution, from that population. How that works internally, don't worry about it. Internally, it's creating an array of values that is normally distributed and then allowing you to randomly sample from that with probability being distributed according to the normal distribution. So there's more likelihood of picking things in the middle than picking things on the side, right? Because that's the normal distribution. Okay. Now, this has only 3 arguments, which is pretty neat. Location, they use the same notation, same bad notation as scipy. Location, that's going to be the mean value. Scale, that's going to be the standard deviation of the normal distribution. And size is going to be how many, the size of your sample, okay? Or something more advanced. We'll talk about size in a second. But first, I want to determine what I need my sampling distribution, my normal distribution to be. I am going to choose a standard normal distribution for simplicity. Why? Because the standard normal distribution, I'm interested in the variances, okay? And the standard normal distribution has a variance of 1, okay? So think about this for a second with me. I have a normal distribution, mean 0, I don't care about the mean. The standard deviation of all variance of the normal distribution is 1. Then I draw random samples from that. Okay? What is going to be the mean? Okay, I draw random samples from that, and then compute their variance. What is going to be the mean of those variances? What did you say? 1, right? Because those random samples, they have a similar distribution as the normal distribution, and their variance is going to be close to the original variance of the population. So the mean of the variances is going to be should be equal to the variance of the original population. The mean of the variances of the samples is going to be equal to the variance of the original population. So that's something we want to test once we run this. Okay? All right, so we're going to do location equals 0 and then scale equal 1.0. Now, what about size? All right, so let's look at size. Size, this could be an integer or a tuple of integers, could be a number. So if I tell it, give me 5, it's going to pick 5 numbers that are normally distributed. Give me 10, it's going to pick 10 numbers that are normally distributed, okay? Or I can tell it, give me 1,000 samples of size 5. So there's going to be an array of 1,000 by 5. Or 100,000 samples by 10. So it's going to give me 100,000 samples of size 10 each. Does that make sense? So here, instead of doing a for loop and running the for loop 100,000 times, and each time collecting a sample of size 5 and putting that in an array, I can just provide here that I want you to create an array, 1,000 rows and 5 each, or 10, whatever my sample size is. Okay? So let me first just demonstrate to you that what happens here. If I put size equal 5 and then print samples, it's going to give me 5 numbers. Okay? 1, 2, 3, 4, 5 that are normally distributed. If I put 10, it's going to give me 10 numbers. Okay? Now what if I put 10, it will give me 10 numbers. All right. Now what if I put a two-dimensional array? I'm going to do 10 by 2. It's going to give me an array of 10 samples. Each sample has 2 numbers in it that are normally distributed. Each sample is normally distributed. Okay? Each sample is normally distributed. So if I do 10 by 10 or 100 samples of size 10 each is going to give me an array of 100 by 10. So what I can do here is put number of samples times sample size. Now this is going to give me, I'm not going to print this, because this is going to give me an array that has 100,000 rows and 5 columns. Do the whole thing in one shot. Beauty of Python. Okay, great. Okay, so now we got our samples. Now it's time to compute. Okay, so generate samples from a normal distribution. All right. We're not done. Now next step is to compute sample variances. So now for each sample, for each row in that array, I want to compute the variance. Okay, so how many variances in total am I going to have? I have 100,000 samples. Okay, each sample is of size 5 or size 10. For each sample, I'm going to compute the variance. How many variances am I going to have? 5. I have 100,000 samples. I need to compute the variance for each sample. How many variances am I going to have in total? 100,000 variances, right? That's what I'm doing. For each sample, I need to calculate the variance. So I'm going to have an array that has 100,000 variances. And that's the array that I'm going to create a histogram for. Now remember, the histogram is calculating how many numbers, how many values belong to each bin, to each category. So on the x-axis of that histogram is going to be the variances going from 0 to 10 or whatever, or 100. And in each bin, it's going to count, okay, the first bin from 0 to 0.1, how many numbers do I have in my array that belong there? It's going to put the count, and it's going to bin it and create a nice histogram for us. All right? So how do we compute sample variances? Remember, we do that with NumPy as well. So sample variances. Okay, compute sample variances for each sample. There is one variance. Okay, so sample variances is going to be mp.var, if you remember that routine from NumPy. So that routine computes the variance of the array of elements, all right? And then we have this argument here called degrees of freedom. We said that's 0 when you are dealing with the population, and it's 1 when you are dealing with samples. So we have to put DDOF equal 1, okay? Okay, so let's see what this gives us. mp.var, and I'm going to give it samples, and DDOF equal 1. Okay? Now, I want to double check that print sample variances.size. I want to check that the size is 100,000. Okay? Sorry. Huh. So it turns out that when I did this calculation, so if I print sample variances, it didn't do what I wanted it to do. It like did the variance of all variances twice. It's like gave me one number. I should expect 100,000 values, not one value. The problem is we missed an argument over here. And that's kind of usually rarely the case in most NumPy operations. But when you're dealing with 2 and 3 and 4-dimensional arrays and so on, you have to pay attention to this argument called axis. This is going to tell numpy.var routine along which axis or row or column. If you think of the array instead of row and column, think of it along axes. So the rows are one axis, the columns are another axis. If you have 3-dimensional array, you're going to have 3 axes and so on. We want to calculate variances, okay, not across all the rows, but across the columns, right? So for each row, we want to do the variance across the 5 columns or the 10 columns. So we have to tell NumPy, we have to tell that to NumPy. So my axis here is going to be actually just equal to 1. Now when I do this, there you go. Sample variances, the size of sample variances is 100,000. So what it did now, if you print sample variance, it's going to be a huge array. Print sample variances. It's going to be a long array, but it contains. So let me reduce this. Let me do 100 samples. Okay. So sample variances now is an array of 100 values that contains the variances of each sample. This is the variance of the first sample, variance of the second sample, third sample, and so on. Okay. And it is going to be a 1-dimensional array because we don't no longer have columns anymore. All right, so let's go back to, let's keep this at 100. I've done this before, so I'm comfortable doing 100,000. But when you're like experimenting with things like we did in numerical methods, start easy so you don't blow up the memory in your computer and end up in some infinite loop or something. Start with a reasonable number to make sure things are working, and then we can test at larger numbers. So that's just good practice. Okay, so now let's go ahead, and so now we verified. Okay, so this is verify that sample variances is the correct size. All right, so now it's time to do a histogram. plt.histogram. What are we histogramming about? It's the sample variances, right? We're going to take that sample variances array, and we're going to histogram it. I'm going to do 80 bins. And I'm going to turn it into a density so that it gives me a probability type answer. So density is true. And I'll give it a label, let's say sample variance. Okay. Let's see. All right. Okay, so it gave us something. It's like all over the place. Right? Okay. Now I know that this is because I have only 100 samples. Okay, so I'm going to go to 100,000. Now I see something happening. Okay, it's a distribution. Okay, what is the x-axis? Is the sample variance. What is the y-axis? It's the probability or the number, the frequency of how often you're going to get a variance close to 0 or this variance or that variance, right? Now, when you look at this distribution, first let's make sure you got it in your plots so you can focus with me. in our knowledge of how we interpret graphs, is this a symmetric distribution? It's not a symmetric distribution. So that rules out the normal distribution immediately, right? Kind of rules it out. And especially for small sample sizes, which is a reality. We always are dealing with small sample sizes relative to a population. It's something different, right? It seems to be skewed to the right, and most of the concentration is around what value? What did we want to test, right? It's around the value of 1. Because the mean value of the sample variances should be equal in the limit to the variance of the original population. The original population has a variance of 1, so the variances of the samples should have the same variance. In other words, their mean value is the same variance as the original population. Mind twist, okay? But it's not a normal distribution. It's not symmetric, okay? It has a tail and it peaks. All right, so let's play with this a little bit. I'm really hating this array, so I think this is coming from the histogram. I'm going to put a semicolon here. Okay, that's better. Okay, so now let's do sample size of 10. See what happens. Okay. Change the sample size. Oh, it shifted. Feels like it shifted. It's more centered around 1 now, but it's starting to get less skewed and more symmetric, right? With more symmetric. So, okay, let's do one more. Let's do 15. Again, it's shifting. Let's do 30. Okay, oh, this is starting to look like a normal distribution. Not quite, but it's starting to look like a normal distribution. What I can conclude from this is that the distribution, the sampling distribution of sample variances, this thing is highly dependent on the sample size. We did not see this with sample means. The sample means didn't shift. They stayed under the curve. They just started approximate. They were always symmetric, and they started approximating the normal curve better and better. This one is changing its shape. And that shape is changing based on the sample size. So if I want to develop a theory to represent the sampling distribution of sample variances, what is that distribution? I know from just observation that it is going to be dependent on the sample size n. Okay, let's drive n higher. Let's go to 100. Ah, look at that. This is more and more normal. And indeed, as n approaches infinity, we do get a normal. We do recover the normal distribution. But anything outside that, for any finite sample value, it is not a normal distribution. There's always an error if you draw if you do the normal distribution. Okay. In fact, the distribution of sample variances only when drawing from a normal population is what we call the chi-squared distribution. Okay? It's a theoretical distribution result from the central limit theorem for sample variances. So we say that the sample variances, when drawn from a normal population, are distributed according to the chi-squared distribution. Now why am I introducing the chi-squared now? Because that is going to be critical when we do our first statistical inference in 15, 20 minutes. Okay, so we need to know about this distribution. Okay, so let me introduce it and then plot it on top of this so that we can see that things work actually. All right, so when the population distribution is normal, then this variable, chi-squared, equal to sample size minus 1 times sample variances squared, so S squared, remember, is the sample variance, over sigma squared, which is the population standard deviation. That chi-squared, that new variable, follows what is called a chi-squared distribution. And the chi-squared distribution, you don't need this formula We just use built-in formulas, but I just want to give it to you how it looks like. It's this complicated formula for the chi-squared distribution. There's the theoretical way to derive this. K is the number of degrees of freedom, which is n minus 1, or the sample size minus 1. And I think in your homework, I'm going to actually give you a problem to prove why we need n minus 1 in the sample variance rather than n. Okay? That was always a question. And gamma is the gamma distribution, which for when x is an integer, this becomes the factorial. But in general, this is the gamma function. Okay, so this chi-squared, which is a new random variable based on sample variances. So the sample variances, they are a random variable. We're drawing random samples, and they're distributed randomly. If you create this new variable, that variable is distributed according to the chi-squared distribution. Okay? It's distributed according to the chi-squared distribution. So let's see if we can demonstrate that. Excuse me. If we can demonstrate that with Python. Okay? Give me a second. Okay. So to get the chi-squared, now I'm going to have to use a little formula here that I don't expect you to know. It's a little bit advanced in the derivation, where you don't have to worry about it, but just to make the chi distribution fit this distribution, be truthful to this, I have to just make a little correction, not a correction actually, just something true from theory. So now I want to plot the chi distribution on top of this and show you that it is consistent with this plot. So plot the theoretical chi-squared distribution. So let's create a lin space, mp.linspace, and let's say, excuse me, we're going to go from, let me see, so I have 1 to 1.8 over here. Let's go from 0 to 5. Okay, 0 to 5, put like 1,000 points in the lin space. And then I can grab the chi-squared distribution from stats.scipy.stats. So chi PDF is equal. Remember how we did the normal distribution? Similar thing, we go to stats dot, there's a chi2, okay? Chi2, you grab the chi2 and you call the PDF. All right, now the arguments here for the chi2, well, I'm surprised that they have an API help. All right, so, but it has x and a bunch of arguments, which is useless, right? So here's how this is going to work. I'm going to plot it, okay? My x value, and don't worry about why this is the case. But that comes from theory, sample size minus 1. So I need to scale it by n minus 1. And then I need the degrees of freedom for the chi-squared distribution. So if you remember theoretically from the slides, where are the slides? Okay. So if you remember from theory, the chi-squared distribution has a parameter called k. And it's the degrees of freedom. So when we start using the chi distribution in Google Sheets, it's going to ask you degrees of freedom. What is that? That's always sample size minus 1. Okay, so I need that when I declare it in Python. So I'm going to declare degrees of freedom, df, is equal also to sample size minus 1. All right. And I also need to scale this by the sample size minus 1. This is just kind of some math that's a little bit beyond what we need to know for now. But just so that I can plot it and it is the correct scaling on the plot. And then let's plot, plt.plot. We want to plot chi PDF versus x. Now my x values are these s squared values, okay? These s squared values. Okay. So chi PDF, and then we'll do it in red. Okay, and then we put label theoretical distribution, theoretical result. Okay, and then plt dot legend. Unmatched. Who is unmatched? Oh, here. Here. What is it? Sky PDF. How? I have an extra one here, right? Ah, look at that beauty. Okay, so let's go to 5 samples first. Look at that. 5 samples, chi-squared distribution. If you plot the normal, it's not going to work at all. 10 samples is going to move with it. Let's put 10. Look at that. It's moving with it. It is indeed a true theoretical result. The sampling distribution of sample variances, when drawn from a normal distribution, is distributed according to a chi-squared distribution. Okay? And you can go to even 100 samples. It will always work. It always works. Okay, now the reason I had to do the scaling is really because of the way I'm plotting things. So chi-squared is normally is distributed according to the chi-squared distribution, not s squared. But on my x-axis, I have s squared. So I need to adjust that with the n minus 1 to be able to get the population correctly, to get the scaling correct when I plot it. Anyway, don't worry about that. It's just a demonstration. But the simulation is still valid, even if you don't plot the chi distribution on top of the simulation. Now, once we know this result, we're going to trust it with our heart and just move and mind, whatever. And we're going to move on. Okay? But this is the demonstration of that theory. Now, this is a problem. Because when the population is not normal, you don't get necessarily the chi distribution. Okay? When the population is not normal, you don't get the chi distribution. We can test that in a second here. Let's try. So I'm going to go and pick an exponential distribution. So I'm going to copy and paste this here. The exponential distribution is simple in that it needs only a, let me move this out of the way. So if you do numpy.random dot exponential, no, dot py.random dot exponential, the draw samples from an exponential distribution. The exponential distribution only has one parameter, which is the standard deviation. Now, I want a standard deviation of 1, just for simplicity. So I'm going to put scale equal 1, and then size the same as before. Okay? So now I'm drawing samples from a exponential distribution, not normal. Chi distribution still stays the same, but then see what happens. These sample variances, they don't follow the chi distribution exactly. It's approximate, but it's not as beautiful, as correct as the result for when drawing from a normal distribution. This is important stuff because your knowledge of this, you're going to understand when you're reading a statistical analysis. How did they use the chi-squared distribution? Their population is uniform. Did they account for that error and that mistake? And if they didn't admit it, then they are at fault. They're being dishonest about the analysis. That's why you need to know this. Now, more samples doesn't make it better. Go 20. It's still the chi-squared overshoots. Go to 50. It's not there. It's a huge error. Okay? It's a huge error. So unfortunately, the result for sample variances is not as universal as the result for sample means. The chi-squared is only true when the when the population distribution is normal. Okay, so what are we going to do in this class when we're dealing with this? We're still going to use chi-squared for large numbers of samples and accept that there's an error there, because anything we want to do other than that is going to require another 2 courses to do some more advanced statistical analysis. to understand how we do it for non-normal populations. Or we will be dealing mostly with normal populations, which is, a fair thing. A lot of populations are normally distributed. So it's a fair assumption, okay? But know that there's an error here, okay? Know that we are committing a grave mistake here, okay? Truth in advertising, I guess. All right, so we will use the chi-square distribution, especially for large N, and we will be dealing with a lot of normally distributed populations. This is the end of the CLT. Now you will notice that this is in chapter 8. The CLT is in chapter 7, but I'm pulling this from chapter 8 because they're wrong in the book to put it in chapter 8. They should put it here, okay? And so I put it here, but this is discussed in chapter 8, okay? 8.5 specifically. Okay, let's take a break before we start with statistical inference. Let's resume. We are now ready to start on the third unit, statistical inferential statistics. We kind of took a major detour with probability, start descriptive statistics, finally inferential statistics. It's a very big world. A lot of contentious debates, a lot of open-ended questions, things that you might think you got right, and then somebody comes and gives a different interpretation. It requires a lot of expertise, a lot of knowledge, a lot of reading, and this is only a first step in that direction. But obviously, it will hopefully get you to understand some of the lingo so you can make slightly more informed decisions, or you can, pretend that you know a little more and that you understand things when you read a study or a report. So the purpose of inferential statistics, I had a kind of picture alluding to this at the beginning of the course, is in practice we cannot study an entire population. It's impractical, it's expensive, it's impossible. We can only study samples, and if we are choosing a simple random sample, equal likelihood of everyone being chosen, good representation of the true population, then the question is, what can we infer about the population by only studying the sample? That's why we studied the CLT, because the means of the samples and how they're distributed is going to tell us what can we say about the population and with what confidence or probability. Okay? So the sampling distribution of sampling means is a probability distribution. And from that, we will be able to make statements that about the population that we can say the mean of this population is this much with this much error, or this much probability of or likelihood, or confidence, or p-value that you hear a lot about, or p-hacking if you haven't heard of that, which is a statistical trick to make studies fit a certain agenda or story. Terrible practice, unfortunately. So far, we've learned that sampling distributions of the sample means are normally distributed, and that was the standard central limit theorem. And if your sampling distribution of sample means is represented by x bar, I'm using lowercase here, it could be a capital letter, but x bar is my random variable that corresponds to sample means, then we expect that the mean value of sample means to be equal to the mean value of the population in the limit as n approaches infinity, etc., and that the standard deviation of the sample means equal to the standard deviation of the population over square root of n as n approaches infinity. And then we said, well, there's a cleaner way of representing these normally. So x bar is normally distributed. That's the sample. That's the random variable of sample means. And then we can create a z-score to simplify this and convert it into a standard normal distribution. So this z value is also normally distributed, and it's the sample mean minus the population mean over sigma divided by square root of n. Okay? So we know this. And now the question is, okay, if I only have the sample, so mu x bar, can't we just say that the population mean is mu and the population standard deviation is square root of n times the sample standard deviation? Can't we just say that? Hardly. Unfortunately, no. Because these statements are the math that you see that mu x bar equal mu, that's in a limiting sense. Okay, this is not any sample you draw, you're going to expect its mean value to be equal to the mean value of the population. And the fact that the sample means have a distribution tells you that there is variation in those means. Okay? So what if you pick a sample in the tail or a sample in the middle, right? They're going to have different mean values. So the estimate of the mean of the population comes with an error if we're using the sample means. And that's what the beginning of inferential statistics tells us about. So we can certainly say that the mean value of the sample means is close to the true population mean with an error. What is going to help us define that error is the sampling distribution of sample means. That's why we looked at those before doing this. Okay? So we will be dealing with two situations in this chapter, is when we try to estimate population means with known population standard deviation, which is really a silly case, because if you know this population standard deviation, you will know also the population mean. Okay? But it's just a simple case to get us thinking about estimates. Okay? Now the real deal is when we try to estimate a population mean from sample means with unknown population standard deviation. So you know nothing about the population, neither its mean nor its standard deviation, but we're looking to estimate the mean of the population. We're only focused on the mean of the population. All right, so this chapter will deal with what we call confidence intervals. Who's heard of confidence intervals? Like, 95%. This result is with a confidence interval of 90%. What does that mean? So we'll hopefully learn about this in this chapter. We'll do a few things. These objectives will change. We'll see how they change. You'll be able to define and compute what we call point estimates, determine the best point estimates for population parameters, calculate margins of error for confidence intervals for population parameters. So, and also in other words, what is a confidence interval? Construct confidence intervals for population parameters. We're going to be dealing mostly with means. We'll look at variances at the end. And then determine the minimum sample size required to obtain a desired level of precision. So one of your colleagues asked the question, how do you estimate the sample size? Well, this will help us. This type of analysis will tell you if you want to estimate, we will be able to say, if you want to estimate the population mean with a margin of error of 1 centimeter, okay, error in some measurement, then you need a sample size of 78. We will be able to get those numbers. Okay? All right, so we will start with estimating population means with a known standard deviation. That's the simplest we could do. It's very academic. It's impractical, but it does teach us how to build confidence intervals before we get to the more complex case where we don't know sigma. Now, every time I say estimating population means, it implies that I'm using information from a sample to do that estimate. So I know what the sample is telling me. What can I infer about the population? And I have the same slide over here. Okay. So let's start with some definitions. Bore you with some definitions. So for a given population parameter, like mean or variance, standard deviation, which is similar to variance, or other properties, but mostly mean and variance, there are a couple of estimates that could be used to estimate that parameter. Primarily, those are called point estimates and interval estimates. Duh. Okay. A point estimate is simply a single numerical value for a parameter. So I'll give you an example. I draw a sample of people. I'm looking at population heights at the University of Utah. I sample this class. I get your heights, and I take the average. And I use that to say, hey, this is a point estimate of the average population at the average height of the population at the University of Utah. That's it. Just a simple point estimate. So in other words, here's another example. If I'm given these numbers for the population mean of test scores on a standardized biology exam, whatever this example came from. Okay, so this is a random sample taken from that population. Okay, now the question is, what is the average test score for that population? The simplest estimate you could give is the mean of the sample. Because we know in the limit that the sample means are going to approach the population mean, right? The average of the sample mean is going to approach the population mean. So, you know, like I said, can't we just do this? Yes, you can do this. It's called a point estimate. It doesn't quantify the error in your estimate, though. But it's a very quick way to make an estimate about the population. Okay. Here's another nasty definition. I'm going to talk about estimators. Okay? An estimator, theta hat, of a given parameter theta. So an estimator, x bar of a population, x bar, which is a sample mean of a population parameter mu, okay, is said to be an unbiased estimator. This is a very important definition. If the expected value of the parameter is equal to the true value, okay, so if the expected value of the estimate, hold on, this is a hat, I had a typo here, take value. So this says, in estimator theta bar, so that's a number that's estimating a parameter. It's a number could be estimating the population mean, the population variance. We say that that estimator is an unbiased estimator if its expected value, so what's the expected value? You need to remember those definitions. Integral of x of the f of x, etc., right? So the integral of theta hat times the distribution, okay, over the entire support. Okay, so is an unbiased estimator if its expected value, E of theta hat, is equal to the true value of the parameter. The expected value measures that in the limit when you can do it over an infinite number of samples and sample sizes, your expected value in the long run is going to be the true value of the parameter. So we call that an unbiased estimator. Okay, it's not going to show up a lot now, but it'll show up later. Okay, we will use words that, oh, this formula is an unbiased estimator of the population standard deviation. Okay, and then you need to understand, what do we mean by an unbiased estimator? Oh, it's not biased. No, it means that the expected value is equal to the population parameter. Okay, I'll give you an example. So I put a little example here. The expected value of the sample means is equal to the population mean. Okay, so let me prove this for you. You're going to have a homework problem similar to this, but on the variance. So prove that the sample mean is an unbiased estimator of the population mean. So consider a random variable x from a population with an expected value mu. So we know that that population has a property, has a mean value of mu, or its expected value is mu. For n simple random samples, show that the following estimator, x bar, which is the mean of the sample, the summation of the values divided by the number of samples, right? The summation of all x's divided by n, show that this x bar is an unbiased estimator of the population mean. Very simple. You apply, and you can use this notation because this E is an integral. And that integral is a linear operator. So E of x bar, you just substitute what x bar is here. It's 1 over n summation of x's, right? Now, because this integral can commute with the sum, it's a linear operation, so you can bring it to the inside. So you get 1 over n times the summation of the expected value of xi. Now, what is the expected value of xi? It's mu. Summed n times gives you n times mu, divided by n gives you equal mu. So x bar, or the mean of the sample, is an unbiased estimator of the population mean. Okay? The standard deviation of the sample is not an unbiased estimator of the standard deviation of the population. And that's going to be left for homework. Okay? There's going to be a square root of n involved. Right? So things will start coming better together with this kind of math. Okay. Now, okay, so we have an unbiased, the idea of the unbiased estimator. Now you can connect the unbiased estimator to a point estimate, in that your best point estimate for a parameter needs to be an unbiased estimator. That's it. The best point estimate is going to be an unbiased estimator. Otherwise, you're going to be biased. Okay? So when you're asked to do a point estimate, figure out what's an unbiased estimator. I don't know what those are. You might develop your own formula. You might be given a formula, and you'll have to prove that this is not a good point estimate. It has to be an unbiased estimator. Now, we can do better. Using only one value to estimate the population mean or any other population parameter leaves a lot of room for error. Okay? Now, because we're dealing with means right now, because we have the distribution of sample means, we can actually assign an error to any point estimate we're making, from the samples about the sample mean. And so what I have here, what would be much better is when you give a point estimate is to give a range of values with a probability or likelihood that you can, how much confidence do you have in that range, in those values. So instead of giving a point value, saying the mean value is 15.5, you could say, well, the mean value is somewhere between 14 and 15.5, and my confidence in this is 95%. Okay? So that will have a meaning. That's what we will learn here. Okay. An interval estimate, another definition, is simply a range of possible values for a population parameter. Because we don't know the population parameter with 100% truth. We only know it with a likelihood. So we can provide a range of values for the population mean. The height of the population is going to change between 5'8" and 6 feet, right? Somewhere in that range. I don't know what it exactly is, but I know it's going to be somewhere in that range. All right, 3 more definitions. Okay, so we have the point estimate, unbiased estimator, and then the range, what a range is. I mean, you understand what a range is. Now, 2 important terms here. The level of confidence and a confidence interval. The level of confidence, which we are going to call C from now on, is the percentage of all possible samples that will produce the interval estimates containing the actual parameter. It's a weird definition. Keep it for a minute there until we get to this example so you understand what it means. What's more important is a confidence interval is a range or an interval estimate associated with a certain level of confidence. So for example, the population mean value with a confidence interval of 95%. So for example, a 95% confidence interval level means that if we repeated our sampling process 100 times, we expect that 95 out of 100 confidence intervals to contain the true population mean or any other parameter. So when I say I'm estimating my population mean with a confidence interval of 90%, it means if we were to repeat the sampling randomly 100 times, 90 of those samples are going to have the same confidence interval. Okay? That's a very important result. So level of confidence is something that you are going to choose. You're going to say, I want to estimate the population mean with a level of confidence of 90%. Then your next question is going to be, what is the interval? What is that interval with that confidence level? Okay? Finally, and this is where the final result is, so the confidence interval itself is just one value. It doesn't give you the range of values for your parameter estimate. Okay? The parameter estimate is derived from the confidence interval, and it's defined as the margin of error, which is the maximum error or the range that your estimate is going to take. So forget all the definitions. If my point estimate is here, using the confidence interval, I'm going to be able to find a plus and minus value, okay, for the range of my point estimate. So this could be average height point estimate is 5.7 plus or minus 6 inches. Okay? How do we get those plus or minus? They are going to come from the confidence interval, which is based on the level of confidence you're going to define. Okay, it's a little bit, a lot of definitions, but examples are going to make it straight. Okay, we haven't even talked about population mean, so we'll start with some examples here, how to build a range. A college student researching study habits collects data from a random sample of 250 college students on her campus and calculates that the sample mean, okay, is X bar equal 15.7 hours per week. Okay? If the margin of error for her data using a 95% level of confidence is E equals 0.6 hours, construct the 95% confidence interval for the data. So here we're given the error, 0.6, that will, so an error of 0.6 hours per week will produce a confidence interval of 95%, and then our result will be reported as 15.7 plus 0.6 to or minus 0.6. So my estimate of the population mean of the college students, how much time they're spending per hour to study, is somewhere between 15.1 and 16.3 hours. So we report it this way or this way. This is called our confidence interval. Okay? Now here I gave you E, and the error, the range, and I gave you the confidence interval. Okay, so it's kind of a little silly example. Okay, because I'm giving you E. What is more powerful and the real deal is how do you find E for a given confidence interval? Okay, you got to keep up with all of those definitions and all of those words. Statistics has a lot of jargon, man. It's incredible. Okay, so the real deal is really when you figure out the error margin for a given confidence interval. Okay, in this previous example, I just gave you the error margin, so you know how to build a range, which is kind of simple. Okay, so how do we find E? How do we find that range for the point estimate? So we know from the central limit theorem that the sampling distribution of sample means has the same mean as the population. Okay, that's kind of what the CLT tells us in the limit. Now, this property suggests that using the sample mean X bar as an unbiased point estimator of the population mean. Okay, good. So we got the point estimator. That's obvious. The sample mean is a good point estimate, and it's an unbiased estimator of the population mean, but I need a range. Now, recall that the sample means also, they have a distribution of their own, and they have a variance, they have a standard deviation. Their standard deviation is sigma over square root of n. So there's a possibility of variation in those sample means. So we're going to use that to define the interval. Okay? So this is where what we did in chapter 6 is going to come in very handy when we calculated areas under the curve. I'm going to assume you remember all of this, especially after exam 1. So I'm not going to spend time explaining what we're doing here. I'm going to assume that you know how to do it. Okay, so now remember that the sampling distribution of sampling means is normally distributed, and we can define the z value for sample means to get a standard normal distribution, because then it standardizes everything, nice and easy. So we define that as X bar minus mu over sigma over square root of n. Now, remember, what are we after? We are after mu. We don't know what mu is. We don't know what it is, the population mean. Okay? We know X bar, and we're assuming that we know sigma in this case. Okay? But we don't know mu. We're trying to estimate mu. Also note that X bar minus mu, what is that? That's the error committed in using X bar to represent mu. Agreed? Mu is the true value that we're after. X bar is our observed value. Their difference is nothing more than the error. So keep that in mind, because that's gonna be the key to finding what E is. Okay, so we're gonna do some geometry and algebra over here just to get to a way to finding E. So I have 10, 11 minutes. I should be able to cover all of that. Okay, so let's put this on the side. Now I'm going to ask you a question. What does the following area in pink represent? But what does that mean? What does this area between the bounds represent? The what? Okay, a little bit, so dumb it down for me a little bit more. So that's, yeah, so let's remember. What are we plotting on the x-axis? It's our z value. It's x bar minus mu over sigma divided by square root of n. Okay, that's a standard normal distribution. Okay, I have two values here, minus ZA and plus ZA. What does this area in pink represent? It is a confidence interval, but specifically, what does that mean? What is the area under? Okay, so Daxon, you said loyalty, loyalty, the probability. Oh, I thought. Yeah. Okay, the probability of what value? No, z. The probability. So the x-axis contains x bar minus mu over sigma by square root of n. Remember, we're after mu. Okay, we're after mu. And specifically, x bar minus mu is an error. So what this area in pink here represents that the probability that x bar minus mu over sigma divided by square root of n is between minus ZA and plus ZA. Agreed? That's by definition of the area under the curve, right? This is, we did this when we did continuous probability, right? This C is the probability that this quantity is between those two values, minus ZA and plus ZA. Okay? Simply the area between those two bounds. Keep in mind that I'm after x bar minus mu. I'm after finding an error here. And this is the first step. Okay? Now C actually, as your colleague said, represents our level of confidence. So in other words, when I make this statement, I can say that whatever C is, let's say you pick a value for ZA and ZB, and you end up with C, minus ZA and plus ZA, and you end up there equal ZA, because this is symmetric. Let's say you end up with C equal 0.95. Then you could say that the probability of this being between those values is 95%. So I have that much confidence that this quantity is between those two values. Right? That's how I build confidence. Okay? Okay. So now I need to do some finagling or manipulation. Used to have a handyman, he would always say, oh, we need to finagle it into place. Like, what is you finagling? It's like, put it into place. I once discovered he was putting some tiles in our bathroom, and so one of the tiles was at an angle, and I saw that, and I called him. He said, yes, I'll finagle it tomorrow into place. I was like, okay. Right, so I need to finagle this math a little bit just to standardize the nomenclature. So I want to call the areas in blue, the areas on the tail, I want to call those alpha. So this area plus this area, I'm going to call that alpha. Okay? And we also know that, therefore, C is 1 minus alpha, right? Because the total area is 1. If these are alpha, then whatever is left is 1 minus alpha, and that's C. Now, this is statistical theory, why they do it this way. Has a lot of historical reasons. But C, we're going to call C the confidence interval, but we work internally with what we call alpha. Okay, go figure. Okay, so for example, if C is 0.95, then alpha is 0.05. So if C is 95%, alpha, the total area in blue in the two tails, is 5%. If C is 99%, then alpha is 1%. Now, in general, in practice, we work with C rather than alpha. We say that our confidence interval is 95%. We don't say that alpha is 5%. Nobody knows what alpha is. Okay, so just focus on the confidence interval. but we will need alpha to do internal calculations. Okay, so that's why I'm introducing that. Okay, one more thing. We also know that the area in blue is equal here and here. So this area is equal to this area. Agreed? Because it's symmetric. If the total area is alpha, then each one of those is what? Alpha over 2. Right? So let's call that area alpha over 2 and alpha over 2. Now you find out the mystery for having these lines here. Okay, for alpha over 2. And then instead of ZA, for convenience, we're going to call this point here minus Z alpha over 2, and this point Z alpha over 2. Okay? Now remember, this is centered at 0, right? Because this is standard normal distribution. So this is called minus Z alpha over 2, Z alpha over 2. And alpha is the area in the tails, right? On both tails. And C is 1 minus alpha. Good. All right. Now these Z alpha over 2 and minus Z alpha over 2 are called the critical values for your confidence. So when I ask you, get me the critical values for a confidence interval of 90%, I'm asking you to find Z alpha over 2. Now once you find one of them, you find the other because it's symmetric. Okay? Now, I'm asking you this. Can you find the Z values corresponding to the following C values? If C is 99%, can you describe how you'll find Z alpha over 2? Do you know? You should know. Can you explain that to me? How you would do it?
You do 1 minus 0.99 and then divide that by 2.
It gives you alpha. It doesn't give you the Z. It doesn't give you the Z. Even divided by 2. So how do you find the Z value? Nicholas? Yes, thank you. Okay, you need to remember that, what he said. Say that again. Inverse of the Z-score. Okay? So remember, alpha, or alpha over 2, is nothing but the area. Remember our tables? I'm asking you, find me Z minus Z alpha over 2 for the area of alpha over 2. You go look in the table. What is the probability that it's alpha over 2? What is the corresponding Z value? In Google Sheets, you find normal.distribution.inverse. You plug in what? Alpha over 2 in it. And it's going to give you minus Z alpha over 2, which automatically gives you Z alpha over 2. It's easier to find minus Z alpha over 2 because it's the area to the left. Okay, that's what the tables and the things give you. Okay. So in this case, alpha is 1%. So it's easier to find minus Z alpha over 2. And then you do a reverse Z-scores on alpha over 2, which is 0.05. You can plug that in your Google Sheets, and then you get the value for Z. Now, these Z values are general. For any case, when I'm talking about sample means, for a confidence interval of 99%, Z alpha over 2 is always 2.575. For a confidence interval of 95%, Z alpha over 2 always 1.959 because that's the standard normal distribution, right? So we're going to keep those with us so we don't have to recalculate them every time, okay? All right, I have 2 minutes, so we're almost there. Okay. So now I've updated my formula. I have my probability that x bar minus mu, my estimator, minus the true population mean, over sigma over square root of mu. Is mu equal to 0? Tell me. This is standard normal distribution, and it's centered around 0. Does that mean mu equal to 0? No. This quantity has a mean value of 0, but mu is not 0. What I'm plotting here is this whole thing, which is another random variable. But mu itself is not 0. Neither is x bar. Okay? Pay attention to that trick question. Okay, so now I've updated my math. Minus Z alpha over 2, Z alpha over 2. Okay? Now we need to find the upper and lower bounds for x bar minus mu. So recall that x bar minus mu is nothing more than the error committed in estimating mu using the sample means x bar. So if I take this, what's inside the probability here, and I finagle it mathematically a little bit, I can extract, look at this, I can extract a range for mu values based on my point estimator x bar minus z alpha over 2 sigma over square root of n plus z alpha over 2 sigma over square root of n. Those are your bounds for the interval. So all you need to know is your z alpha over 2 based on your confidence interval. Okay? And then from that, you get your error bound, which is z alpha over 2 times population standard deviation over square root of n sample size. That's all you need. You say, I want to estimate the mean with a confidence of 90%. What is z alpha over 2 that corresponds to a confidence of 90%? You get z alpha over 2, you multiply it by sigma or square root of n, and it gives you the bound. Okay? And anyway, that's our result. We'll resume on Tuesday. Okay? We'll resume on Tuesday. Review your material so you don't fall back. A lot of jargon, a lot of words, a lot of formulas. Okay? Thank you. Godspeed. Have a great weekend.